It's now 5:30, July 13th, and it's time to start our class. We are in chapter 10. We actually had a missed meeting on Wednesday of last week due to a storm, and I asked you to watch a video from 7-7. If you might have watched the video from 7-7, then you should be up to speed. If you went further and watched 7-9, then some of this is going to be a rehash, and that's fine. I would ideally had preferred everybody to watch 7-7 and 7-9, but I didn't ask anybody to do that. So we're going on from there. And that means we're starting off with example 10.3. And I'm going to go ahead and share my screen just as soon as I find out whether Sam has a question. Sam, do you have any questions before I get started, bud? And feel free to type it. Can you hear me, Sam?
Yeah, can you hear me?
Yeah, I can hear you now.
Yeah, I was just about to say something. I thought there was something wrong with my headphones.
Gotcha. Well, last time I taught the whole class without my headphone on, so
Oh, okay.
it wasn't very good because luckily y'all can still hear me according to some of the students, but I couldn't hear any of y'all, and I was like, man, they are really not replying today. And then I realized, well, yeah, you're not wearing your headphones, so I'm a bit of a goober that way. So, you don't have any questions though before we get started, bud?
I do have some at the end. It's
Okay.
just for like the tests and also the comprehensive lab tests that we may have.
Hmm. Yeah,
Um, but
we're not. You're. Are you in my lab? Yeah, that's right. You're 01B. So yeah, you're in my lab. We are not having the comprehensive lab final, so y'all are off the hook
okay.
on that one.
All right.
The lab reports as I've been grading them are going fine. I should get some more graded again tomorrow. That'll help you guys. Also, I want to mention this is for your class as well as the N02B class. I spent the weekend remaking all my tests banks, which is really a nightmare because there's like 30 of them and there's about 2,000 questions total. And I had to make them all this weekend because y'all are getting these responses where the images aren't showing. I have had two students told me that they stopped using, in one case, it was they stopped using Google Chrome, and then another case it was they stopped using Firefox. But in one case they went to Microsoft Edge, and lo and behold, it worked fine. So if you're having problems with the images loading, at least one student found that when he switched to using the browser Microsoft Edge, it worked. And then another student said that they hadn't had any problems, and that student was using Safari, which is a Mac product. So if you use those two browsers, either Microsoft Edge if you're in the Windows world, or Safari if you're in the Mac world, then maybe you'll have better luck with the pictures showing. But that being said, I'm getting ready to erase all of my banks, and then I've renamed the new banks exactly the same names, and I'm going to import those in tonight. So we might have everything working again. If I find out that that ended up going into place, but then you guys couldn't access the test, then I'm going to have problems and I might have to introduce another practice test. I'll keep track of the old practice test. So if you already scored 100 on it, you're good. You've already got your 100. But you definitely need to take the other one because the other one will have the pictures rendering themselves properly, and that should also help with the actual test. Even though the midterm, I mean the face-to-face test that has to happen this week, that shouldn't be affected because the way I loaded it, it's basically a regular test, and I choose a particular question, and that one seems to work for me. Of course, if you do have a problem, you need to let me know. So luckily, I'll be able to see it from the screen as well. So that was just a message in case anybody had it. Remember, try Microsoft Edge for your browser and try Safari for your browser, and maybe that'll get rid of the photo problem where your practice tests are not showing the photos properly. It might not work, but still. And like I said, tonight and or tomorrow, I'll be posting, getting rid of all my test banks and then putting in new test banks in hopes that that'll fix it all. So now let's go ahead and get started. I'm going to share my iPad screen with you folks, and we're jumping into chapter 10. And specifically, we're starting off with chapter 10 and conceptual example 3. But before I do that, I wanted to remind you of the equations that we came up in the 7-7 lecture that you were supposed to watch in lieu of class on Wednesday. So this is a rehash of those equations, and the left-hand side is the linear equations that we learned in chapter two. The middle slash right-hand column, that's the rotational analog, and you can see V mapping to omega, X mapping to theta, T goes to T. Then we see A mapping to to alpha, and from that, you can get basically the exact same equations. And all of that stemmed from this third column on the right, which is S equals R times theta. And if you go on the assumption, excuse me, if you go on the assumption that the R is going to be a constant, then you end up getting the ds over dt is equal to R d theta over dt, and d theta over dt is omega, and ds over dt is v. So that's how we get v equals R omega from S equals R times theta. And similarly, if I take the derivative of v with respect to t, I get a. And if I take the derivative of r omega with respect to t, assuming r is a constant, then I get d omega dt, which is alpha. So I get a equals r times alpha. That's critical to know as well. And those equations are valid whenever, for instance, something's rolling without slipping. Then the actual arc length it traveled is directly or is exactly equal to the radius times the angle through which it turns. Not only that, the velocity tangentially, the v velocity is equal to r times omega, the angular velocity. And then finally, a is equal to r times alpha. All of that happens when you're doing rolling without slipping. And then these other equations down here, these are your dynamical equations that we learned. For instance, this is the first version of Newton's second law we learned. And you can see that when you let F become tau, the torque, then M becomes I, the moment of inertia, and A becomes alpha, the angular acceleration. Similarly, the other version of Newton's second law that we learned, F equals dp dt, becomes the summation of the torques equals dl dt, where L is R cross P for at least a object that's small compared to the radius or the excuse me, compared to the radius from which the thing is orbiting. And we could also say in magnitude, L is equal to the moment of inertia times omega, which is exactly analogous to P is equal to mv. And K being 1/2 mv squared becomes K equals 1/2 I omega squared. So when something's actually moving like this, it's 1/2 mv squared as the kinetic energy. But if it's moving like this, then it's 1/2 mv squared for the center of mass of the thing, but it's also 1/2 I omega squared because the thing's rotating about its center of mass. So that's the key thing to understand. Now we can go ahead and jump into conceptual example 10.3. Conceptual example 10.3 says, is the lion faster than the horse? On a rotating carousel or merry-go-round, one child sits on a horse near the outer edge and another child sits on the lion halfway out from the center. Which child has the greater linear velocity? So with V equals R omega, which you can see right here, this is what we call the linear velocity, and this is what we call the angular velocity. The omega is the angular velocity, the v is the linear velocity, and you see that the v is related to the omega by multiplying the omega times r. Okay, so when you're talking about a horse that's out near the edge, then r is the total radius of the carousel. But when you're talking about a lion halfway out, then r is 1/2 of the radius. So that tells you that from this formula alone, the horse being at a bigger R should make it having a little bit larger V, but that depends on how omega is related for each of them. So what I want to point out is generally we're talking about rigid objects. So we can take this, for instance, Rubik's Cube face as a rigid object. And I want you to notice that right now that's blue, white, white is up. Notice if I turn it 90 degrees, now it's blue, white, white, 90 degrees. That means every part of it turned by exactly 90 degrees. So when you're talking about a rigid object, like a carousel, for instance, it rotates throughout the whole body through the same angular distance. In this case, theta would be 90 degrees. Now, that's just the S equals R times theta part. But we need to address the V equals R omega part. So I just covered that. Obviously, the distance when I went like, well, actually, I went from this way, blue, white, white. So the distance traveled by the blue, obviously, is the distance from the center to the center of the blue times the angle that it rotated through, which was 90 degrees, which of course has to be pi over 2. So it's pi over 2 times r, say, is the distance moved by the blue one. And then if you compare the distance moved by this white one, that distance is the same as the distance from the center of the white to the center of the blue, but it's at a different location. But notice when it turns 90 degrees, now this one has moved the distance of that same distance times the 90 degrees, which is the pi radians. So you see that the arc lengths in this case, because they happen to be the same distance, were actually the same. But if you compared, for instance, the outer edge of the blue to the inner edge of the blue, then the inner edge of the blue is only a half of a Rubik's Cube away from the center. So I do half of a Rubik's Cube times pi for how far the blue edge right here moved. But if I wanted to do or excuse me, the blue edge up here. If I wanted to rotate and figure out how far the far edge went, well, that's half of a Rubik's Cube square plus another half. So that's twice as big. And when I multiply that by pi, we see that this edge of the blue moved twice as far as this edge of the blue, and that's because it's twice as far out. So that's sort of like this edge is like the horse, and this edge is like the lion. Okay. But the key thing to understand is the angular turn distance was the same for both of them. They both turned through a radian measure of pi. Now, when you consider the velocity, what you need to think of is the same sort of figure, but now let's say it moved from theta equals 0 to theta equals pi in 1 second. Now that means the average velocity is the pi times the radius over the second, and the average angular velocity is pi over a second. So you see, in that case, the omegas are going to be the same, just like the thetas were the same. And if you go further to the acceleration equals r times alpha, you'd see that the alphas are going to be the same as well. So the angular measures do not change for a rigid body. And that's something to keep in mind. So when we're looking at this particular question on a rotating carousel or merry-go-round, one child sits on a horse near the outer edge and another child sits on a lion halfway out from the center. Which child has the greater linear velocity? Greater linear velocity. Well, the velocity is equal to r, the distance from the center of the carousel to the location of the animal that they're riding, times omega. Well, omega, as I just showed you, was the same for both of them. So we now see that in one case, for instance, the horse, it's r times omega, but in the other case, the lion, it's r over 2 times omega. So that means the child on the horse has a greater linear velocity, and the child on the lion has a lesser linear velocity. If you answer part B, which says which child has the greater angular velocity, you'd have to say neither, because both of them have exactly the same angular velocity. For instance, 90 degrees per second, or pi radians per second, or something like that, if we were treating it as if it were the Rubik's Cube. Any questions on that? All right, so we've got all those formulas, and I also want to point out that A total is equal to A, what we would call tangential, or linear as well, plus A rotational. So when we're breaking down velocities, we not only have a component that is tangential to the motion, and that's why we call it a tan, we also have a component that's perpendicular to the motion, which would be a radial. And you recognize a radial is normally v squared over r, so you'd say a sub r is equal to a sub rotational, which is equal to v squared over r like that. Well, if you remember, v equals r omega, so that means I could replace the v with r omega, and r omega in parentheses squared becomes r squared omega squared over r. So that actually gives us r times omega squared. So that's another version of AR, the rotational angular acceleration. Or excuse me, the rotational acceleration radially. I don't know why I said angular. All right, now let's look at example 10.7. I'll just mention in the conceptual example down here that V horse implies R is equal to the total radius, whereas V lion implies R is equal to the total radius over the whole radius divided by 2. But omega horse is equal to omega lion. Therefore, if I combine these two, I see V lion is equal to R over 2 times omega, because since they're the same, I'll just call it omega. And V horse is equal to R omega. So you see that V horse is equal to twice V lion. But as I said, omega horse equals omega lion. So that was the total result of the conceptual example 10.3. And that brings us to example 10.4, which is what I'm doing now. So example 10.4 says angular and linear velocities. A carousel is initially at rest at t equals 0. It is given a constant angular acceleration, alpha equals 0.60 radians per second, which increases its angular velocity for 8.0 seconds. At t equal 8.0 seconds, determine the magnitude of the following quantities: A, the angular velocity of the carousel; B, the linear velocity of a child located 5.5 meters from the center point P in figure 10.8b; C, the tangential linear acceleration of that child; D, the centripetal acceleration of the child; and E, the total linear acceleration of the child. So I need to write down what we have here. The carousel is initially at rest, and that means V0 is equal to 0, and it also means omega 0 is equal to 0. Uh, we also have it is given a constant angular acceleration, so alpha is equal to 0.060 radians per second, which again is easier to write radians per second squared, but I still want you to think of it as radians per second per second. And we're going to say delta t is equal to 8.0 seconds, because that's really the part that we care about. For part A, they're specifically asking us for the angular velocity of the carousel, so they want to know omega equals question mark. We already learned that for a rigid body like a carousel, which remains rigid unless it spins so fast that the metal starts to fail, in which case it wouldn't be rigid anymore. So we're just going to assume it's rigid. And then part B says the linear velocity of the child, and they say for r equals 5.5 meters for child, v child, which equals VC, is equal to question mark. And then part C, they want to know the tangential linear acceleration. So C, they want A tangent equals question mark. D, they want the centripetal acceleration. So A sub R is equal to question mark for part D, and this again for the child. And then E, they want the total linear acceleration, E, A total, which we just talked about a second ago. So that's what we're shooting for here. Solution. What we know is, for starters, we want to know omega, And of course, we can figure out what omega is because we know the equation omega equals omega 0 plus alpha t. That's the equation that will allow us to figure out that. And we know alpha. We also want to figure out the v for the child. And in that case, we want v is equal to r times omega. And we also want for the a tangential, we want a tangential is equal to r times alpha, and we want a radial is equal to either omega squared r, or it could be uh, v squared over r. And I'm trying to use the little r here instead of the big R. And then, of course, like I said, a total is equal to a tangential plus a radial, and those are vector quantities. So we'll go ahead and proceed as we expected. So first, we're wanting to know omega. Omega is equal to omega 0 plus alpha t. That's going to give us 0 plus 0.060 radians per second times 8.0 seconds. And obviously, 8 times zero point zero 0.06 is going to be 0.48. And that is radians per second because obviously one of the seconds canceled out, and that is our omega, which we were asked for part A. So now for part B, we want to know V. So for part B, I'm going to say V is equal to R times omega. So at that 8.0 seconds time interval, we've got omega is 0.48, and that gives us that V is equal to 5.5 meters times 0.480 radians per second. And this one, we could actually, multiply it by hand, but, using the FOIL method and all that stuff's kind of messy. So I'm going to take it and do the calculator work. So 5.5 times 0.48 is going to give you 2.64. And that turns out to be, in this case, notice I just dropped the radians. Remember, S equals R times theta is what defines radians. And if you solve for theta, you get S over R. Well, as the equation works, the S and the R are supposed to have the same unit. So S over R should be unitless. And that's what a radian is. It's a pure number. So we can drop them when we need to, and we can add them when we need to. So I'm going to drop it here, and we're going to get 2.64 meters per second is the tangential velocity for the child. Okay, and that's part B. Again, ask me any questions if you have them, but I'm going to keep plugging on. And you feel free to stop me. You can just speak out or whatever you want. I need to make sure the chat is visible. I did that. Okay. Even though it's just one of you guys, but all right. So part C now. Part C is we want to know a tangent, and a tangent really means r times alpha. So that's really what we're talking about. Again, they did say for the child, the tangential linear acceleration for the child. So we know the radius is going to be 5.5 meters, and we know alpha is going to be 0.48. 5.5 meters is right. We know alpha is going to be 0.48. Ooh, oh. I just used omega. That's right. Okay. Phew, scare me. Okay. I did use the proper thing for part B, but I almost used the wrong thing for A. For A tangent equals R times alpha. I actually need to know what alpha is in order to figure out A tan. And of course, alpha we know is 0.060 radians per second, up to at least the 8 second mark. And we're asked actually at the 8 second mark. So we're going to say zero. Oops. We're going to say 0.060 radians per second. again, easier to write as per second squared. So I'm going to take 5.5 and multiply it by 0.060, and that's going to give me 0.330. And again, we end up getting something where we can just drop the radians, and this is meters per second is equal to a tangent. And of course, that's for the child. So I'll go ahead and subscript it ILD as well. Oops, like that. And that is our answer to part C. For part D, they want to know the radial part, and this is a perfect example of why it's good to have a couple different ways to calculate it. We know that A radial is V squared over R, and that's also R times omega squared, and I'm going to use the R times omega squared. So the R is going to be 5.5 meters. The omega is going to be 0.48 radians per second, like that, but we got to square it. So 5.5 times 0.48 squared gives me 1.26, 1.27 roughly, with one extra digit. That's 1.27, and that's radian, or excuse me, that's meters per second is equal to A sub R, the radial one. And that's part D. Now all we have to do is figure out for part E, we want A total. So we've already figured out the magnitude. And if you imagine, for instance, that this is the arc the thing is following, something like that, then you might realize that what we have here is a acceleration in the tangential direction right here, which is A tan equals 0.330 meters per second. And then we have 1.3, which is essentially four times as big. And I'm going to say that that's going to be like this. And that's A radial is equal to 1.27 meters per second. And that means specifically, since these two vectors are to be added and they're tail to tail, that means the total acceleration vector, A total, is that quantity right there. Now, normally I calculate the angle between the A tan and the A total, but I noticed your book actually calculated the other one, so I'll do the other one this time. So we're going to call that phi. And first off, we need to get the magnitude. Obviously, the magnitude of A total is pretty straightforward. That's just Pythagorean theorem. So A total is equal to the square root of 0.330 meters per second squared plus 1.27 meters per second squared. And that's going to give us, and I got to be careful with the sig figs here when you're squaring these things and then adding them. Remember, whenever you add or subtract numbers, the sig fig rules are a little different, so you have to look at them. So when I take the 0.33, which I know has two sig figs, and I square it, that becomes 0.1089. And I know it only has two sig figs, so that tells me the two sig figs are actually only good to the second decimal place. So this is going to be 0.1089. That's meters squared per second to the fourth. And I wrote it that way so we'd see exactly where the sig figs are. Now I'm going to do the same thing with the 1.27. And when I square that, I get 1.61. And that's enough. That gives me one extra sig fig. I could get, say, 613 if you wanted, like that. And that's meters squared per second to the fourth, like that. Now, in this case, it was also two sig figs, so that means it's only good to one decimal place once we add them. So the addition of these two numbers uh, 1.6129 plus 0.1089 gives us the square root of 1.7218. But by the sig fig rules, that means only the 1 and the 7 are sig figs, and that's meters squared seconds to the fourth. And then once I take the square root of that by raising it to the zero point 0.5 power, I get again only 2 sig figs. So 1.31 meters per second is equal to A total. Okay. So there's the magnitude of A total. We have that. And now I need the actual direction because A total is a vector quantity. So what we do now is we say the tangent of phi is equal to opposite over hypotenuse and opposite over adjacent, and the opposite is 0.330. I'll leave off the units, and the adjacent is 1.27, again leaving off the units. And that tells us that phi is equal to the tangent inverse of 0.330 over 1.27, like that. So I'll take shift tangent inverse 0.33 divided by 1.27, and this gives me 14.5 or 14.6 degrees, which we should round, of course, to the nearest whole number, and that's going to be, in fact, only 15 degrees, which is exactly what the book is telling us. Any questions on that one? Okay, so looking at our answers, 0.48, 2.6, 0.33, 1.27, 1.31, and 15 degrees. So they all match. I want to remind you, so let's do this with a little line down here just to separate this from the previous problem. I want to remind you, I say remind you, I've mentioned it before, but let's recap. When we're talking about rotational motion, we can talk about things orbiting. For instance, a planet could orbit a star, in which case you have a revolution, and then you have a planet rotating on its axis, in which case you have rotation. Okay, both of those have quantities associated with angular motion. They for instance have an angular velocity, a tangential velocity, but they also have a period, and one's a period of revolution and the other one's a period of rotation. But the main thing to remember is that period t is period, and it's actually measured in seconds or years or something like that, but it's actually 1 over the frequency. F, on the other hand, is the frequency, and frequency is basically the number of cycles that occur in a given second, whereas the period is the number of seconds a single cycle occurs in. Notice the wording there. The period is the number of seconds that it takes a single period to occur, and the frequency is the number of cycles that occur every second. And because of that, you should be able to make out that frequency has to be 1 over the period, or period has to be 1 over the frequency. Now, frequency is in cycles per second, so I'll write that here by saying the units of the period are like the second, or just any unit of time. The units of frequency are cycles per second, which is sometimes called CPS. So you might find old books and old, for instance, military manuals that'll have CPS as the unit for frequency. But in fact, for a long time, since roughly the 1860s, 1870s, somewhere around there, we've been calling this the hertz. And I should mention that one cycle is essentially equal to one revolution, and that's equal to 2 pi radians. Okay. Because of that, you can see that omega is equal to 2 pi times f, because the 2 pi is just converting the cycles to radians, because there's 2 pi radians per cycle. So these are equations that are very important. Frequency is 1 over the period, period is 1 over the frequency, and omega is equal to 2 pi f. And of course, if you're talking about revolving, like the moon revolving around the earth or the earth revolving around the sun, then you also have that the velocity of such a revolution is equal to 2 pi times the radius over the period. And that comes in handy as well, which this is where I was saying we're repeating this information because I gave you some of this information when we covered Kepler's laws of planetary motion and Newton's law of gravity. Any questions on that before I move along? All right, let's look at example 10.5 now. Example 10.5 says, given omega as a function of time, a disk of radius r equals 3.0 meters rotates at an angular velocity omega equals 1.6 plus 1.2 t in parentheses radians per second, where t is in seconds. At the instant t equals 2 seconds, 2.0 seconds, determine A, the angular acceleration, and B, the speed v, and the components of the acceleration A of a point on the edge of the disk. So what we have here is r, the radius of the disk, is 3.0 meters. We have omega, the angular velocity, is given by 1.6 plus 1.2 times t, and all of that is measured in radians per second. Because the time is in seconds, that means the 1.2 must obviously be in radians per second, or excuse me, radians per second squared, because then when you multiply it by seconds, it would spit out that radians per second. And the 1.6 must be just pure radians per second. Though we didn't ask you any of that, I just wanted you to be aware of that and the things that you have to do when someone gives you an equation like this. You got to think, okay, what does the units of 1.6, what are they? What's the units of the 1.2? Because later when you go to, use something from this result, you're going to have the 1.2 there and it's going to be multiplied by something, and that's the way you'll figure out what the units are. So just remember, in this case, since 1.2 times t came out as radians per second and t is in seconds, the 1.2 must be in radians per second. And the 1.6, which is by itself, came out in radians per second, so that means the 1.6 has units of radians per second. Now, what they want to know is t equal 2.0 seconds. In part A, they want to know v at t equals 2.0 seconds. And then part B, they want to know the components of the acceleration at a point on the edge of the disk. So they want to know A tan and A r equals question mark 4 r equal to 3.0 meters. And that's because they told us at the edge. Okay. So how do we go about doing this? Well, we need to figure out the angular acceleration. And we know, for instance, solution alpha is d omega over dt. So that is a way that we can get the actual acceleration out of the omega as a function of time. But we also want to know the velocity at 2 seconds. And we know that v is equal to r times omega. And actually, I should just use a little r, but we did call the radius big R. So using the little r just shows that's the general equation instead of an equation that just happens to work for this big R. We also know that a tangent is the r times alpha, and we know that a radial is omega squared r, it's v squared over r, either one of those. Let's start off with part A. We want to know what v is, and in order to know v, we need to know omega, And specifically, we need to know omega at 2 seconds. So at t equals 2.0 seconds, omega is equal to 1.6 plus 1.2 times 2.0 seconds, and all of that comes out in radians per second. But as I told you, the 1.2 would have to be radians per second per second. So 1.2 times 2 would be 2.4. 2.4, excuse me, 1.2 times 2 would be 2.4. And then 2.4 plus 1.6 would be 4.0. So this gives us 4.0 radians per second is the omega that we're looking for. And now that we have that omega, we can say that V is equal to R times omega, which equals 3.0 meters times 4.0 radians per second, and that gives us 12.0 meters per second is the velocity equals v at t equals 2.0 seconds. So that's what we were asked for, and now we've gotten that. Now for part B, we want to know a tan and a radial. So for part B, a tan is equal to r times alpha. And alpha, of course, is what is the acceleration. And in order to figure out alpha, we've got to take the derivative. So alpha of t is equal to d omega over dt, which would be d by dt of 1.6 plus 1.2 t, and the derivative of 1.6 is 0. The derivative of 1.2t with respect to t is 1.2, and that tells us that it's going to be 1.2 radians per second, which is, again, part of the reason I wanted you to think about what the units of 1.2 would be. So now that we have exactly what the alpha is, and that alpha, by the way, is a function of t, but in this case, you see there's no explicit t, so it's that acceleration at all times. So with that in mind, we can say a tangent is equal to 3.0 meters times alpha, which is 1.2 radians per second, and 3 times 1.2 would be 3.6. So we get a tangent is equal to 3.6 meters per second per second. Oops, I left off the second squared there. So that's a tan. And now I can say a radial is equal to omega squared times r. So I'm going to write that in any order I want. I'm going to and write the 3.0, and then the omega we found was in fact that quantity, but we want that quantity at 2 seconds. So the omega that we found at 2 seconds was 4.0 radians per second. So this is going to be this times 4.0 radians per second is the actual omega that we found, and that's going to be squared. So now we're going to say 16, because 4 squared is 16. 16 times 3 would be 30, 48. So this is going to be 48.0 meters per second per second. Any questions on that? All right. So that's how we do example 10.5. Now, your book talks about the vector nature of angular quantities, and I just want to point out what that is. When something is rotating, there's really no good direction that you can immediately think of for this. For instance, if this Rubik's Cube is rotating like this, uh, you might think of the vector representing the rotation as pointing this way. But someone else would say, well, why is that any better than this way? And why is that any better than this way? And why is that any better than this way or this way or this way or this? All of these directions are equally useful and therefore not useful at all when I'm talking about this thing rotating about this way. But if you choose to make the vector quantity perpendicular to the face that's rotating, in other words, parallel to the axis of rotation, you could make it either this way or this way for this thing rotating this way. So that reduces the ambiguity down to just two choices. So by default or by convention, we use a right hand rule. And what we do is we imagine that our fingers curl around the direction that this is rotating. So if this is rotating this way, then I use my right hand and my fingers are curling around the same direction that this is rotating. So I use my right hand and that removes the ambiguity. So angular quantities are going to have a direction that we can assume that it has, and they're going to be given by a right hand rule. So let me show you what I mean by that with a specific example. Sorry, I dropped into my child mode where everything is like Puschetti instead of spaghetti. So breaking this off, what you could imagine, for instance, is if an oval, and actually, you know what? Let me use my software to make this look better. So if this is the disk of some sort and it's actually rotating this way, then the right hand rule would tell us that the appropriate direction would be this. So we could call, for instance, that the omega vector because it's rotating consistent with the right hand rule in that direction. Similarly, if we drew another oval, another disk rotating, actually, let me go back to using the software, making it nice and neat. Now, in this case, we might say that this particular disk is rotating this. Oop, nope, I want to say it's the other way. We might say that this particular one is rotating that way, in which case I have to turn my hand like this to make my fingers curl in the direction it's curling. And in that case, we get omega is that way. So that's the way our right hand rule works. We can use that for torque. If something's causing a rotation this way, then the torque would point out at me. But if it's causing a rotation this way, then the torque would point away from me, that kind of thing. But I should go a little further and remind you of the next section, which is reminding us that these vectors are actually called axial vectors or pseudo vectors. So these vectors are axial vectors are pseudo vectors vectors, and pseudo means not, basically. So pseudo means not a vector, and they're not a vector. In fact, the reason why is it turns out that vectors have to have certain properties. For instance, they have a magnitude and direction. They've got to obey those rules that I told you about that you learned in pre-algebra when a times parentheses b plus c is equal to ab plus ac. That's one of the rules. All those different rules, a plus b is equal to b plus a, all those different rules are things that make a general concept of an algebra. And the world in which vectors are defined is the vector algebra world. And in that guise, then those things have to be met. Well, one of the things that it does is that they have to be able to transform in certain ways. And one of the ramifications of the way they transform is that an object that has a vector, when you look at its reflection in a mirror, it should have the exact same vector. These don't have that. So let me show you what I mean. Let's imagine again our little disk like this. And let's say this little disk is rotating this way. According to the right hand rule, that means this vector for this one should be that. Now let's imagine that this is in fact in front of a mirror like this. Now, when you look in that mirror, oops, I needed my special drawing skill. When you look in that mirror, it's going to see this rotation happening in this direction. In other words, the part of the disk closest to the mirror is going down. Therefore, the part of the disk in the reflection closest to the mirror is also going down. And in that case, if you use the right hand rule for that particular disk that the front is going down, then you end up getting the omega vector points that way. So in the reflection, it points the opposite direction as it does in real space, and that means that it's not behaving like a vector. So because of that, we call it a pseudo vector, and that means there's certain rules that could cause problems and certain things that could cause problems. It's mostly not going to be an issue unless you actually major in mathematics or if you major in, for instance, physics and go on to theoretical physics, specifically in particle physics, group theory, stuff that's related to quantum mechanics and things of that sort. That's the areas of mathematics and physics in which this would cause a problem. So unless you happen to go highbrow into, if you decide to major in engineering, and then you go to the PhD level as opposed to just a bachelor's degree level, then there's a good chance that you'll run into calculus on manifolds and group theory and stuff like that, in which case that would become relevant. But if you're not doing any of that, this is never going to bother you. Okay. But now you've at least heard that there's an issue with regards to these vectors that are associated with rotational motion, that they're not truly vectors. And there's rules about when things are truly vectors, they behave certain ways. And this obviously violates those directions. So, with that in mind, we're going to move on to the equations. Specifically, the section that we're doing next is 10.3, and that's constant angular acceleration. But I've already discussed that by showing you all those equations. And we learned, of course, the constant acceleration ones are, and actually I've confirmed this since I taught last week, we know that omega average is the same as omega 0 plus omega 1 over 2, as long as you're dealing with acceleration being a constant. But in this case, it's the alpha equals a constant for those to be true. Whereas the left hand column, it was the A had to be constant. In the right hand, or the middle column, if you will, the alpha has to be a constant for all these to be true. And that does include that lowest equation. So I want to extend this a little further. Okay. But now that we have that, we can go ahead and use that to solve problems, which is what example 10.6 is going to be. So let's look at example 10.6. Centrifuge acceleration, example 10.6. A centrifuge rotor is accelerated for 30 seconds from rest to 20,000 revolutions per minute. What is the average angular acceleration in radians per second? Per second, that's part A. And in part B, through how many revolutions has the centrifuge rotor turned during its acceleration period, assuming constant angular acceleration? So we said a centrifuge rotor is accelerated from rest. That means omega 0 is equal to 0. Omega final is going to be 20,000. And it's some ambiguity as to whether you should call this omega or F when we say revolutions per minute, because it's not really in radians, which is what I'd prefer to restrict my omega quantities to, but it is in something rotational, so it's really not A either, or excuse me, it's not V either. But this is RPMs, which equals 20,000 revolutions per minute, like that. So that's really what that is. And what we want to know is in part A, we want to know the average angular acceleration. So alpha bar is equal to question mark. And then part two, we want to know through how many revolutions has the centrifuge rotor turned during its acceleration period. So what we want to know really is sort of delta theta, which would be theta minus theta zero, but we can always define theta zero to be zero. And we're going to say this should be theta in revolutions, because there's some ambiguity with that. If I solve for theta, one thing I know about these equations that I just showed you is they'll definitely work when I use theta in radians, omega in radians per second, and alpha in radians per second per second. But whether they're going to work in revolutions per second and revolutions per second and all that stuff, it remains to be seen until you start plugging the values in with the quantities you have and stuff of that sort. So you got to pay attention to that a little bit. Now, let's start off with what equations we're going to need for this. So solution, we're going to want to find out what the average acceleration is. So the average acceleration we remembered from linear motion was v minus v0 over t. So alpha is going to be, our alpha average is going to be omega minus omega 0 over delta t. It's really just delta omega over delta t, just like A average was delta v over delta t. So we can use that. And then we can use something for theta. That something for theta, we could in principle use omega squared equals omega 0 squared plus 2 alpha theta minus theta 0. Or you could use theta equals 1 half alpha t squared plus omega 0 t plus theta 0. Either one of those would work just fine. The big trick is this revolutions per minute thing being a problem, because one, minutes are not helpful at all because we're almost always using in seconds. And I think that they even give us amount of time. Oh, 30 seconds. So delta t equals 30 seconds. I forgot to write that. I'm going to call that 30.0 seconds, but the zero after the decimal place has an underscore, and that tells us that that is a non-significant figure. Okay, so for part A, we can go ahead and say alpha prime or alpha bar is equal to omega minus omega final. So if you were to just put this number in, you'd get 20,000 revolutions per minute, and then minus 0 over 30.0 seconds. You can see that's not going to work out, but we might wish to keep it in revolutions, in which case maybe I should just convert the units for the minutes, in which case I say 1 minute is equal to 60 seconds, and then that would be minus 0 revolutions per second for the initial. So if I do that, that's certainly fine. I'm going to take 20,000 divided by 60. So 20,000 divided by 60. And that's going to give me 333.3. And at best, we're going to get 2 sig figs out. So I'll assume that the 20,000 was maybe 3 sig figs. And that just is a modicum of conservatism there. So this is going to be revolutions per second in the numerator, and then 30.0 seconds in the denominator. So I'm going to take this 333.3 and divide it by 30, and that's going to give me 11.1. And that's one extra sig fig already, but that's 11.1 revolutions per second is equal to alpha bar. That is a correct answer, but it's not normally the type of correct answer we would prefer. We would normally like it in radians per second or something like that. And in fact, they're asking specifically for it in radians per second, like that. So we can go ahead and convert it at this point, and that'll be fine. So we're going to say alpha prime is equal to 11.1 revolutions per second times one revolution is actually equal to 2 pi radians, like that. And then, oops, and therefore we can get 11.1 times 2 would equal 22.2 pi radians per second. But you might actually want the pure numbers, so I'm going to take the 22.2 and multiply that by pi, so times 3.14159, and that's going to give me 69.8, and that is radians per second is equal to alpha bar. So these are more appropriate values based on the units that they wanted, even though the 11.1 works fine as well. Any questions on that? Now we're going to do part B, and I'll do it with the theta equals 1 half at squared plus omega 0 t first, and then I'll do it the other way. So theta equals 1 half alpha t squared plus omega 0 t plus theta 0. I'm going to take the theta 0 to be 0. The omega 0 was already 0. So that, excuse me, sorry about that. So that gets this a lot simpler right off the get go. So with that, I'm going to go back to my green and I'm going to take 1 half of. Now, we actually wanted this to come out in revolutions, so I'm inclined to use the revolutions. So I'm going to put in 11.1 revolution per second times 30 seconds, which is how long it took. So 30.0 seconds squared. So I'm going to get zero point 0.5 times 11.1 times 30 squared. And that's going to give me 5,000. And that's more sig figs than we really had. But that gives me 5,000 revolutions equals theta. So that's really what we were asked for, and that is the right answer. Now, we can also see that the other equation would work as well. Let me show you how that would be. So if we wrote omega squared, I'll write it in red. Omega squared equals omega 0 squared plus 2 alpha theta minus theta 0, where theta 0 is equal to 0. That would give us theta is equal to omega squared minus omega 0 squared over 2 alpha. So that's going to be omega, which we didn't actually calculate. Oh, the final one. We did actually calculate that. And I'll use the 333.3 revolutions per second, or excuse me, revolutions per second. That quantity is going to be squared minus 0 squared over 2 times alpha, and the alpha we found was 11.1 revolutions per second. Come on, darn it. Revolutions per second. And with that, we get 333.3 squared divided by parentheses 2 times 11.1 gives me again 5,000 revolutions. So you can see that though, of course, the radians is a natural number that works in all these equations, there's a lot of times where you can use revolutions, you can use minutes and stuff like that. But you got to watch out if you're using two different time units in the same equation, that's never going to work out. Anyone have any questions on that? All right. Looks like we're ready to go. So now I'm going to talk about torque, and there's a lot of different ways to talk about torque, but torque is one thing you can imagine as from Newton's second law, we learned that the summation of the forces is equal to mass times acceleration. And the rotational analog is that the summation of the torques is equal to I times alpha. So, with that in mind, just like a force is the thing that causes linear acceleration, a torque is the thing that causes a angular acceleration. So, if you want something to rotate, something to change the rate at which it rotates, even, then what you need to apply is a torque. And when you go to think about a torque, what you want to try to think about is what if I'm trying to, for instance, release a hex nut or to unscrew a hex nut off of something? Obviously, that's something where you're trying to rotate a hex nut, and in the attempt to rotate a hex nut, you're going to have to apply a torque to it. So we're going to use that to argue what torque should depend on. So let me go ahead and draw a line to separate this from the rest of the stuff. And what I'm going to do is picture a little hex nut. So our hex nut is going to be this, 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 something like that. You can see that that's not really that great of a scale or anything, but the main thing is we get roughly. I really want to do a octagon as opposed to a hex nut, but anyways, let's try a better one like this. Let's say like this, and let's say like this, and then this is the bolt is inside of it. The nut is the little thing that's threaded onto it to stop. And then what I want you to think about is we're trying to loosen this. Remember lefty loosey, righty tighty. What do we mean by lefty loosey, righty tighty? Lefty loosey means the top. If you're looking at directly at the object and you want to loosen it up, then you want to move the top to the left. And if you want to move it to tighten it up, then you want to move the top to the right. So that's what we mean by lefty loosey, righty tighty. I'm going to try to loosen this. And therefore, to do so, I am going to use a wrench that happens to fit the size perfectly. And this is the size that I'm going to use. So here's our big wrench coming around this way. And then we're going to imagine that the wrench has a handle that goes way out here like this. Okay. And obviously that handle is kind of weak and pathetic looking. So it's like Olive Oil's legs. Mr. Younger's laughing at a joke that only Mr. Younger gets because he's the only one old enough to even know what Popeye was. But anyways, we'll draw it like this and like this. So when we're thinking about this torque, the symbol we use for torque is this, the Greek letter tau. Okay. And I want to think, what does torque depend on? So I put the alpha in there because the little alpha symbol just means proportional to, even though it sometimes means acceleration. It's sort of the same thing. We're saying this is proportional to, and if I put a quantity to the right of that, like an x, then that says torque and x are thumbs up, thumbs up. If I put an x and then put an exponent of 2 on it, then torque and x squared are thumbs up, thumbs up. If I put a 1 over r on it, then torque and r are thumbs up, thumbs down. Okay, that's the big deal here. Now, what I want to do is first off think, do you guys think a larger force is more capable of loosening a tight nut, or would it mean a smaller force applied to it would loosen a tight nut better? What do y'all think? Feel free to type it in.
A larger force to
Yes.
loosen the nut?
Exactly. A larger force would definitely be more likely to increase it. And that's just, good common sense, obviously. Now, I didn't express anything about what direction, but you can assume that I'm choosing a good direction for that force, okay? So, the next thing is what if we're trying to loosen here, so I'm going to apply the force at two different locations. Let's first apply the force here, F, and then second, let's apply the force here, and I'm going to call this F2, and I'll call this F1. And let's say the magnitudes of the two forces are the same. So the magnitude of F1 equals the magnitude of F2. If that's the case, which one of these locations of application for the force would be more likely to loosen the nut? Would the F2 be a better one, or would the F1 be a better one?
F2?
F2. And that just seems like a natural understanding, right? It's just hopefully y'all have experienced something like this before and you know that you need a bigger what we call a lever arm. Now, I'm going to introduce the concept of a lever arm. The concept of a lever arm is a vector that points from the center of rotation of the object to the point of application of the force, or at least the line along which the force is applied. So, for instance, we can imagine this force is applied along this line, and then R, the lever arm, would be that. So, we're going to say R equals lever arm. It's a vector quantity. And of course, we could also have another lever arm, and that would be like R2 versus R1. And as you said, you are correct. The force being applied at location 2 is infinitely more helpful than the force being applied at location 1. And actually, I shouldn't say infinitely more, it's maybe 10 times more helpful. So in this case, that we now can reach the conclusion that torque is proportional to the force, but it's also proportional to this lever arm quantity. Okay. Now, the only thing that matters beyond this is what's the actual direction of the force. So, for instance, let's imagine applying a force, and I'm going to put it right on the R vector instead of off to the edge like it's been here. We might imagine, for instance, a force that is that, but we also might imagine a force instead that is that. So we could say this is F3, and we could say this is F4. And I think you'd realize that these two quantities would not do the same amount of torque. Obviously, if the magnitude of F4 and the magnitude of F3 were equal, they would not cause the same amount of torque because some component of this purple torque is being wasted. Specifically, this purple torque has a component this way, and then it has another component this way. Notice that small component pointing to the left just tends to push the wrench onto the nut better, but that's about it. And in fact, if we tilted it the other way, it would actually tend to take the wrench completely off the nut, which wouldn't be good. So, what we can do is we can imagine that the angle here between the force and the actual lever arm, if we put those two vectors tail to tail, that force or that angle has a angle that's best for it. In other words, we specifically would like the angle between the force and the lever arm to be exactly 90 degrees. That would be in its max. And what we know is sine theta goes like this, and it has a maximum at theta equals 90 degrees. So what we might do is go ahead and say torque is equal to F times R times the sine of theta. And when we do that, that includes a little diagram like this where F and R are tail to tail, and that's the angle theta. And I shouldn't necessarily put an arrow on that little arc because the angle could go from R to F, R from F to R. It doesn't really matter. Okay. So by doing this, we've now made an argument for what the torque actually is. The torque in magnitude is equal to R times F times the sine of theta. There may be a constant we need to throw in there, but I'm telling you we don't. Okay. So the ultimate result is torque magnitude is equal to R times F times the sine of theta. And if you spent a little time thinking about these various vectors, what you'd figure out is that r times f times sine of theta could also be written as r perpendicular times f because the r times the sine theta would give us the component of r that is perpendicular to f. You could also analyze it again. I don't know why I put equals or plus there. You could also analyze it again and say it's f perpendicular times r because you could treat the f sine theta as one quantity, in which case you'd say, oh, the f times sine theta is the component of f that's perpendicular to r. And you can see that in this drawing right here. For instance, if you want to take this little drawing here, you could say perpendicular to R would be right here. So you could break R down into components that are perpendicular and parallel to F. So if we did that, let's imagine, for instance, the F is this way, like that. And then you could say, all right, well, I have one R component that is perfectly perpendicular, like that. That's R perp. And then I have this other component, R parallel to the force. Now, with that being theta, that means this angle right here is theta. So you can see that R times sine theta gives me R perpendicular. That's why I was able to make that conclusion. You could also do the same thing by breaking F into components perpendicular and parallel to R, and you'd get the same result. So this is actually a valid result that works just fine, and you'd be surprised how this all comes in handy. But all of it points to a more general understanding, and that more general understanding is that torque is a cross product. It's R cross F. So I'm going to go ahead and use this time to teach you how to calculate a cross product rather quickly. So how do we calculate a cross product? Well, there's a bunch of different ways. Okay. For starters, we learned, just like we learned with dot products, we learned that A dot B was equal to the magnitude of A times the magnitude of B times the cosine of the angle between them, which we could also write as A B cosine theta because we don't really have to use that cumbersome uh, absolute value notation to indicate the direction or the magnitude. We can just leave the vector symbol off. Well, there's an equivalent one for the cross product, and it's A cross B magnitude is equal to A times B times the sine of theta. So using that and knowing that is pretty helpful. And that's actually where we got it from. Remember, we first came up with R times F times the sine of theta. So we know originally that that should be R times F times the sine of theta is the magnitude of the cross product. Now, with that in mind, let's watch what happens if I take two vectors, let's say R equals, and remember you can use this less than greater than notation to eliminate having to write the I hat, J hat, and K hat. This could be R sub X, R sub Y, R sub Z, and then F could be F sub X, F sub Y, F sub Z, like that. And that's another way of writing it instead of I hat times FX plus J hat times Fy plus K hat times Fz. We can write it this way. It makes it a little easier. Now, what I'm going to do is say torque is equal to R cross F, and that means R sub X, R sub Y, R sub Z cross F sub X, F sub Y, f sub z, and all things change, of course, if we're not using Cartesian coordinates, but we'll leave that for some other time in a more advanced class. But now what we're going to do is we're just going to do a cross product like we normally would. Now, I wanted to show you that less than greater than notation, but to be honest with you, it's not very helpful here. So I'm going to revert to I hat, j hat, and k hat. So in doing that, I'm going to say rx I hat plus ry j hat plus rz k hat crossed with fx I hat plus fy j hat plus fz k hat, like that. And then I just use the FOIL method. You know, like we learned, a plus b times parentheses b plus or c plus d. That is just the FOIL method. That's what we're going to do here. But because we know specifically how the magnitude of I cross k is and that sort of stuff, all we need is a right hand rule for us to understand what the direction of a cross b is. Because it turns out that if you write a cross B like that, let's say uh, A cross B, then that includes a diagram like this where there's A and like this where there's B, and the angle between them is theta. Then A cross B, it can be given its direction with a right hand rule. And the right hand rule goes like this: you take the first vector in the cross product and it points in the direction of your index finger. The second vector in the cross product points in the direction of your middle finger, and your middle finger can be in all these different angles. The only thing is, if the angle goes to zero, meaning it's parallel to your index finger, then the cross product will be zero. Or if the angle goes to 180, meaning it's anti-parallel to the first vector, then the cross product goes to zero as well. But as long as it's not zero or 180, then all these directions work. And then your thumb points in the direction of the cross product. So I can take my index finger and point it in the direction of A, and then take my middle finger and point it in the direction of B. And what I would see is that I get a vector mutually perpendicular to both of them that points, in fact, in this direction. And that direction is indicated by a right angle there and a right angle there. And that is A cross B. So between knowing that right hand rule for the cross product and then knowing the magnitude is the magnitude of the first times the magnitude of the second times the sine of the angle between them, we can completely figure out what this cross product is just by doing this. I'll give you another way in a second, but this is what I want to show you first. So first off, we're going to take the Rx times the Fx, and it turns out this cross product is what we call a linear operation. So I can pull all the scalar parts out to the left and just let the cross product act on the vectors, in which case the first term is going to be Rx Fx times I hat cross I hat. In that case, I hat cross I hat, we know that they're parallel. So that's this case where I've got these two the same, and we know the cross product is zero. So that one's not going to survive. But now we're going to do Rx times Fy, but this time it's I hat cross J hat, because the Rx was with the I hat and the Fy was with the J hat, and I hat cross J hat, I hat cross J hat points just the same as I hat is the X direction, J hat is the Y direction, and K hat is the Z direction. So this is just K hat. And now I can do Rx hitting the FZ. That's going to be plus Rx FZ times I hat cross K hat. Now, I hat cross K hat, in this case, we really want it to be, let me draw you an XYZ coordinate system so it works a little better. We always use a right-handed coordinate system, and for that reason, I can call this X and this y, and then the right hand rule tells us that this will be z, and that means, of course, that I hat is this way, j hat is this way, and k hat is this way. So if I do j hat cross or I hat cross k hat, then I can see that it's going to point in the negative j hat direction, like that. Now I've done the Rx times each component of F. Now I'm going to do the Ry times each component of F. So I'm going to say plus Ry Fx J hat cross I hat. Now J hat cross I hat, we can say J hat cross I hat. Looking at my little XYZ coordinate system, I see that points in the negative K hat direction. So I put that there. Now I'm going to do RYFY. So plus RYFY. And then, of course, I wrote, oh, it's supposed to be a Y. That, of course, is going to be J hat cross J hat, which is 0. And then RY has to hit the FZ. So it's going to be RYFZ. Only this time it's J hat cross K hat. J hat cross K hat gives me, in fact, I hat, like that. Now I've got to let the RZ hit all the terms of the F. So now it's going to be RZFX. That's going to be K hat cross I hat. And K hat cross I hat gives me the J hat direction. RZ is now going to hit FY, and that gives me K hat cross J hat. And K hat cross J hat gives me negative I hat, like that. And then finally, I have RZ FZ, and that's going to be K hat cross K hat, which is 0. So we can group the like terms. In other words, all the I hat terms go together, all the J hat terms go together, and all the K hat terms go together. And in doing that, I'm going to say the I hat, for instance, is RYFZ minus RZFY I hat. That takes care of this term and this term. Notice I pulled the negative inside on that second one. Now I can do the same thing with the J's, and I get a positive J down here with RZFX. So RZFX minus RXFZ is going to be J hat, and that takes care of this term and this term. And now finally, I got the K hat terms, and that's RX FY minus RYFX, and that just gives me K hat, and that of course takes care of this term. Oops. That of course takes care of this term. And where's the other K hat? Oh, there it is. This term. Okay. So that is a way to do it, and that is a formula for the torque. And you'll see I've got that formula on our equation sheet, so you can just blindly apply the formulas. It's fine, but that's one way you can do it if you don't have that formula. Here's the other way you can do it, and it's a little more complicated. Hopefully, you learned about this method of finding determinants already in your trig class or whatever. But here's another way: torque is equal to R cross F. And the way we often calculate that is by putting it in a matrix and taking the determinant. The first row of the matrix has to be I hat, J hat, and K hat. The second row has to be the first vector component, so Rx, Ry, Rz. And then the third row has to be the second vector, so that's Fx, Fy, Fz. like that. And then to take the determinant, what we do is we can. I'm using multipliers, and the multipliers require this -1 to the I plus j power times, basically when you take that multiplier, you cancel out that row and that column. And for instance, we're going to first expand on I hat, and I hat actually has an ij that is 1 1 because it's in the first row, first column. The J hat has first row, second column. The K hat has first row, third column. Those are the I's and J's that I'm talking about, and it's not to be confused with I hat and J hat. This is just the indices that we're used to in matrices. But what we normally have is -1 to the I plus j power. So when I expand on the I hat, I basically am cutting out this column and this row, and that leaves just this little 2 by 2 matrix. And I have to multiply it by -1 to the 1 plus 1 power because this is 1 and this is 1. -1 to the 1 plus 1 power is -1 in parentheses squared, which gives me a +1, so nothing happens. That being said, here's what we end up getting. We're going to get I hat times +1, and now I've covered up the first column and the first row, and that leaves this little RY, RZ, FY, FZ 2 by 2 matrix. And to calculate a determinant for a 2 by 2, you just multiply these two minus the multiplication of these two. So we do this times this minus this times this. That's going to be RYFZ minus RZFY. So that's the I hat term. Now the J hat term, notice that's got the 1 and the 2 on it. So when I raise -1 to the 1 plus 2 power, that's -1 in parentheses to the third power, and a -1 to the third power gives you -1. So what I do in this case is I actually do the determinant backwards. So instead of going top left times bottom right minus top right minus bottom left, I do it the other way around. I do top right times bottom left minus top left times bottom right, and that takes care of the negative. So let me show you how that's implemented. I'm going to say plus j hat. Now this row or this column and this row disappears, so that leaves me these two guys and these two guys as if they're a 2 by 2 matrix. Normally I would go this times this minus this times this, but because of that -1, I'm going to do this first and then this. So in this case, I get RZFX minus RXFZ. And that takes care of that little minus that I have. And then -1 to the 1 plus 3 is -1 to the 4, so that's a positive power. So I don't have to do any weird stuff like that with the K hat term, but I am going to write plus K hat. And now that I'm expanding upon the K hat, that gets rid of that column and that row. So it leaves this little 2 by 2 matrix. And that when I do this minus this, so I get RXFY minus RYFX. And that is, notice the exact same formula that I got before, uh, only doing it an entirely different way. So there's a lot of different ways you can calculate this determinant or calculate a cross product in general, but that shows you a couple different ways, and hopefully now you know how to do it. Not only do we have torque equals R cross F with the determinants, we also have torque is equal to R perpendicular times F. We also have F perpendicular times R, and we also have R times F times the sine of theta. But when you use those, you got to use the right hand rule to give you the direction, because torque is at least a pseudo vector quantity, and it's supposed to be associated with a direction. So let me move on now and do some calculations so you'll see some example thereof. So if we look at here, we're going to say example 10.7. This one's kind of hard to show, but I'm going to draw a representation of it. So for part A, we're going to imagine the upper arm bone, uh, humerus. Yeah, I think it's humorous. And then what we're going to imagine is a bicep attached, of course, to the little joint, which we're going to picture as this wonderful little circle. And anybody that has any elbow problems knows that this is not completely accurate. But now we're going to have the radius or ulna, and they're actually running parallel, but we're going to treat them as if they're just one object running perpendicular, and we have a nice 90-degree angle and that sort of thing. And what we're going to assume is that this distance right here between the center of axis of rotation to the point of application of the force, that's going to be 5.0 centimeters. Okay. And we're going to imagine that this force that is actually applying F is equal to 700 newtons. And we want to calculate the torque on that. Now, in addition to that, we're going to do part B. And part B is a little different. We're going to have a vertical humerus again. But this time we're going to imagine the radius and ulna as if they're tilted downward at some angle like this. And in fact, what we're going to pretend is that angle is 30 degrees. We still have, in this case, a force acting upward because our bicep, let's do our bicep in red. So our bicep still goes like this and still attaches down here, say. And you could think of it, for instance, as if the distance is 5 centimeters, but that's not necessarily perpendicular. But the main thing is we still have a force upward that is 700 newtons. Okay. And what we're asked to do is calculate the torque in both cases. So what we can do here is solution torque is equal to R cross F. That's not going to be a very handy way of doing it. But the magnitude of the torque is R perpendicular times F, but it could also be F perpendicular times R, but it could also be RF sine theta. And that sine theta is supposed to be done when the two vectors are tail to tail. Okay. So in this first case, A, it's pretty straightforward. Torque for part A is going to be, we can use the right hand rule for starters. So we can say the R vector is that little guy. And then R cross F, like this, gives me the torque out of the page. So the torque is out of the page for this particular vector. And it's going to be equal to 0.050 meters times 700 newtons times, in this case, you see they're automatically perpendicular, so I could just say it like that and leave it be. Or I could say times the sine of 90 degrees. And 5.05 is 5 over 100. So if I take and multiply 5 over 100 times 700, I get 5 times 7, which is 35. So the answer is 35 Newton meters, which your book is calling meter newtons. I don't like that because it's too easy to mix that up with a millinewton. So I'll write it this way. But that's the torque, and it's out of the page for the direction. Okay. Now for part B, it's still the 5 centimeters, but now we have a slightly different scenario going on because the angles are different. So torque is going to be 0.050 meters times 700 newtons, but we need to figure out the actual angle. So in this case, we could say, oh, I could say that the R vector, oops, try to draw it a different color again, and it's still not working. The R vector is actually making a quite big angle. In fact, the angle is 90 plus 30 degrees. So we would actually write this as sine of 30 plus 90, which would be 120 degrees. But if you look at the trig function sine y equals sine theta, what we know is sine theta looks like this, where this is 270 degrees, this is 180 degrees, this is 90 degrees. And in fact, if you go 30 degrees beyond 90, you get to 120. But if you go 30 degrees less than 90, you get to 60. And those two have to be exactly the same value. So with that, you can figure out that this is exactly the same as 0.050 meters times 700 newtons times the sine of 60 degrees. And from that, this is the 120 works. You can go ahead and do that, but I just wanted you to see how it can work out to come out this way. So I'm going to take 35 times the sine of 60, and that's going to give me 35 root 3 over 2, which is 30.31. So we get 30.3 Newton meters again equals the torque, and again, it's out of page. So that's the direction. Any questions on that one? All right, let's do a little bit more uh, complicated example. Maybe it's a little more complicated. I think actually this last one was pretty complicated, but let's go ahead and separate this. And now I'm going to go to example. And in this case, it's example 10.8. And it says torque on a compound wheel. Two thin disc-shaped wheels of radii RA equals 30 centimeters and RB equals 50 centimeters are attached to each other on the axle that passes through the center of each, as shown in figure 1017. Calculate the net torque on this compound wheel due to two forces shown, each of magnitude 50 newtons. So I'm going to draw the picture and I'm going to use the features that this program has, which is going to make my circles quite nice. So my first circle is going to be in this little box right here. So hopefully this will draw a nice circle. Yeah, good enough. And then my second circle is going to be in this box right here. And I'm trying to go 4 wide in each case. So now I'm going to try to go like this. Look. I bumped into my iPad at the last second, and that did not make it helpful. Okay, that looks pretty good. And they look like they're fairly centered. And there you go. Oops, didn't mean to do that. Ah! I'm trying to move this stupid thing. Ah, and it's not letting me. And I'm too obsessive to stop. Please help me. Okay, good enough. Actually, it's not good enough at all. It's really bad, but we're going to deal with it. So the inner one has a force acting this way. And of course, I forgot to take it off the clean drawings. So this is 50 newtons. The other one has yet another angle, and this one's actually at a 30-degree angle. And this force goes like that, and that one's also 50 newtons. However, we do know that one of these is big, and that's the big radius, RB. And RB is 50 centimeters. And the other one is small, and that's RA equals 30 centimeters. They want us to calculate the net torque. Now, what I want you to understand about this is the torque, the 50 Newton at 30 degrees, that's tending to rotate this in a clockwise direction. whereas the 50 newtons down is tending to rotate this in a counterclockwise direction. So the main thing here is we have to realize that these two torques are fighting each other. So one's going to be called positive and the other one's going to be called negative. I'm just going to compute the two and then subtract them, their magnitudes, big minus small, and that'll give me the magnitude. If I took the time to draw an x and y and z axis, then the very vectors would dictate exactly what direction each of those torques have, and it would come out with a very specific positive or negative answer. But in this case, I'm just trying to take the magnitude of it, so I'm just going to subtract the two. So first off, we're going to do torque sub B for the 50 centimeter, and then torque sub A for the 30 centimeters. So torque sub B is equal to the R times F times the sine of theta is what we're using. So the R is 0.50 meters. The F is 50 newtons. And then the angle, remember the actual vector, the lever arm vector, is this guy, and that's going to be what I call R sub B. Now, if you look, you'd see if you put these two tail to tail, then the angle between them would not be 30 degrees. It would actually be 60 degrees. So I'm going to say 0.50 meters times 50 newtons times the sine of 60 degrees. Does everybody follow how that became 60 degrees? Anybody have any questions on that? Okay, zero point 0.5 times 50 is obviously 25 times the sine of 60 is 25 root 3 over 2, which is 21.6 or 21.7 newtons. Okay, that's the TB. And actually, that's one extra digit beyond the sig fig, so I'll do that. Now I'm going to do T, the torque, due to the A configuration. That too is 0.30 meters, but it has the same force, which is 50 newtons. But in this case, you can see that the lever arm vector, R sub A, is actually perpendicular to it. So it's zero point 0.3 times 50 times the sine of 90 degrees. And zero point 0.3 times 50 is the same thing as 3 times 5, and that's 15. So that gives me 15.0 Newton meters, and I left off the meter on the other one. So one of these I have to call positive, and the other one I have to call negative. Either way, the summation of the torques is equal to 6.7 Newton meters, and that's the total torque. Now, it obviously TB, because that larger radius makes a bigger torque, so that's the one that's going to win. And for that reason, it's going to tend to rotate in a clockwise direction. If I use a right hand rule, then that means it's pointing into the board. So I would say pointing into the page. And that's the actual direction of the torque. Uh, and it actually causes clockwise rotation. Any questions on that? By the way, we'd normally call that a negative torque. We one of the things I often use, and I tell you guys to use this in your statics classes too. For instance, you can say this is X and this is Y, and then you can also put something like this and you put plus on it. What that means, and you don't even have to write the X and the Y normally. Instructors all, just about all instructors I've ever run into, all accept this. So if you write this, what this means is positive X to the right, positive Y up, and positive torque is counterclockwise. So I'll say is CCW. So that's what that symbol indicates when you write it like that. It just says, hey, here is my sign convention that I'm using. And since I drew an arrow to the right, I drew an arrow up, and I drew an arrow counterclockwise, that means the X is to the right, the Y is up, and the counterclockwise is the positive direction of torque. Any questions on that? All right. Now we're down to the part where we can actually start solving problems. And in order to do that, I need to give you Newton's second law. And I'm specifically talking about dynamical problems as opposed to just kinematic problems. Remember, kinematics is the motion, studying the motion for motion's sake without reference to how that motion occurred. Whereas the dynamics says, hey, what kind of forces or torques causes these particular velocities, accelerations, and stuff of that sort. So it turns out there's two different ways, and your book goes about doing this. There's two different ways of using the equivalent of Newton's second law. The first one is the summation of the torques is equal to I times alpha, and this is only works when the axis fixed in inertial reference frame. So if you have an inertial reference frame, meaning one that's not accelerating and stuff like that, in other words, inertial reference frame, just remember that means Newton's first law of motion, i.e., Galileo's law of inertia, seems to be valid in that respect. If you have that, then you can just use the summation of the torques about any point is equal to I times alpha, and that all works great. But if you're using a coordinate system or a reference frame that may accelerate, then you got to be a little more careful. And in that case, what we write is the summation of the torques about the center of mass. So that's why I put the parentheses in the center of mass there is equal to the I about the center of mass times the alpha about the center of mass like that. And in this case, it is axis fixed in direction, but may accelerate. So what we mean by that is, for instance, you could have a disc rolling down an incline. Since that disc is rolling down the incline, it's probably accelerating. Well, you can take a reference frame that rides down with that. That's an accelerating reference frame. But because the axis of rotation is sticking out of the page or into the page, either one, that means it's fixed in direction, but it's in an accelerating reference frame. As long as you do the summation of the torques about the center of mass is equal to the moment of inertia about the center of mass, then the equation will work. So that's the key thing to understand here. Now, with that in mind, let's start example 10.9, and that might be the very last one we're able to get. In fact, if I remember correctly, I think that was the last. Yeah, that was the last we were able to get in my other class as well. Hopefully, we can do some moment of inertia calculation too, but I'll try my best to see what I can get. So let's go ahead and separate this from the next example, and the example is 10.9. Oops. Example 10.9, two weights on a bar, different axis, different eye. Two small weights of mass 5 kilograms and 7 kilograms are mounted 4 meters apart on a light rod whose mass can be ignored, as shown in figure 10.20. Calculate the moment of inertia of the system, A, when rotated about an axis halfway between the weights, and B, when rotated about an axis zero point 0.5 meters to the left of the 5 kilogram mass. So let me draw a rotation axis, and I'm going to say over here is 5.0 kilograms, and then over here is 7.0 kilograms, and this distance is 2.0 meters, and this distance is negative 2.0 meters, and our axis of rotation is right there. This is part A. Now, in part B, we're going to do it a little differently. We're going to say this is our axis of rotation. And now I'm going to go over here to 0.50 meters. And that's the distance there. And in fact, I have the 5.0 kilogram mass there. And then out here, 1, 2, 3, 4, roughly here is 4.50 meters, and 7.0 kilograms is there. So for this is part B. Now I'm going to say solution. Moment of inertia is equal to the summation over I equals 1 to n of m sub I r sub I squared. The m sub I is the each individual mass, and the r sub I is the distance measured perpendicular to the axis of rotation to the point of location of the actual mass. So for part A, I'm going to say I is equal to 5.0 kilograms, and then that radius is actually a positive distance of 2.0 meters, and that's going to be squared, and then plus the 7.0 kilograms, and that one's also 2.0 meters from the axis of rotation, and that's squared. So I get 5 plus 7 is 12, and both of those are going to be multiplied by 4 because 2 squared is 4. So 12 times 4 is 48, and that gives me 48.0 kilograms meters squared is the moment of inertia for part I. And you might even say that that's the moment of inertia about the center of mass, except in this case, these two masses weren't the same, so it's not really the center of mass, but it's sort of closer to the center of mass. Now, for part B, we're going to do the exact same thing, but the distances are different. So we're going to start with the 5.0 kilograms, and notice that that is 0.50 meters, and that's going to be squared. And then we have the 7.0 kilograms, only this one's going to be 4.50 meters away. So I'm going to take 5 times zero point 0.5 squared. That gives me 1.25 kilograms meters squared, plus 7 times 4.5 squared. That gives me 141.75 kilograms meters squared. So that's going to give me 143 kilograms meters squared equals the moment of inertia in this case. And really, we had two sig figs, so that decimal place was not a sig fig, and the other one we had two sig figs, so the one place. So technically, this should be roughly 140 far as sig figs go. Again, I don't grade on sig figs, but I wanted you to know how to do it. That's why I carry it out so many times. But that's it. That's how you calculate the moment of inertia. Any questions on that one? All right, now I'm going to calculate the moment of inertia for basically a rod, and we're going to call this Mr. Younger's example, for instance. And I'm going to go ahead and steal it. So I'm going to say right here. Actually, I want to include all this. So I'm going to try to copy this. Copy. Now I'm going to go to here and say paste. So here's my example. And I've actually, because of the way I copied it, I might have got some extra stuff that I didn't really mean to get yet. So I want to erase that a little bit. But we're going to say for starters, solution. Moment of inertia I is equal to the integral of r squared dm. And we learned about this dm before. dm can equal lambda dl r sigma dA r rho dv. Okay. In this case, this rod seems really thin vertically and really thin in and out compared to the length L, like that. So this looks like what we would treat as a one-dimensional object. So we're thinking using dm equals lambda dl. Well, if I look at that, then I can see maybe I consider one spot on the rod, and that spot is right here. That's a distance r away, and I want an infinitesimal differential mass element, and I need the left end of it and the right end of it, whatever's furthest and nearest to the rotation axis, I need them to differ by only an infinitesimal amount. So what I do is I allow the x variable to increase by an amount dx, so that the left-hand side, for instance, would be x, and the right-hand side would be x plus dx. And then I guaranteed that the dm is microscopically large, or microscopically large in terms of the r. In other words, the integrand doesn't change significantly from one side to the other, which is sort of the rule that you have to do when you're doing integral of r squared dm or the integral of x dm, like we did in center of mass. So I'm going to say that little dot down, that little green, purple slice down there, that is going to be dm, and dm is equal to lambda dl normally, but since it's parallel to the x-axis, I'm just going to call it dx. Now, I wrote up here specifically because it's good for you guys to start thinking in terms of lambdas, sigmas, and rhos. What is the lambda, or what is the sigma, or what is the rho? In this case, I'm telling you, since this is a thin rod whose mass is uniformly distributed, then the sigma or the lambda or the rho is a constant. Uniform distribution of mass means those quantities are constant. In this case, it's lambda, and you can get it by just considering the whole thing. The whole thing has a certain mass per unit length. I'm calling its mass big M, and I'm calling its length big L, so the lambda is M over L. Now I can go ahead and calculate it. I is equal to the integral from negative L over 2 to L over 2 of r, the distance from the y-axis is, and the y-axis is the axis of rotation. That distance is actually called x, so I'm going to write it as x squared, and then the dm I'm going to write as lambda dx, and lambda is a constant, so I can pull that out in front, and I get the integral from negative L over 2 to L over 2 of x squared dx, and that gives me 1/3 lambda x cubed from negative L over 2 to L over 2. Now, this is a good time to plug in what the lambda is, so I'm going to write 1/3 m over L, and now I'm going to say L over 2 squared minus negative L over 2, and actually that should be cubed. Sorry about that. And negative L over 2 cubed, like that. This gives me 1/3 m over L times, now I'm going to get L cubed over 8 minus a negative is going to be plus L cubed over 8. So this becomes 2L cubed over 8. So I get 2m L cubed over 3 times 8 times L. And of course, the 8 is 4 times 2, and the 2 is 2 times 1. So this 2 cancels out with that, and I get 1/12 ml squared. And that's the moment of inertia of a rod about its center of mass. which is more than we were really asked for, but I did calculate the moment of inertia. It just happens to be about the center of mass because of the uniformity of it and that sort of thing. Now for part B, we want to calculate it as if it's rotated about the left end. So in that case, we're going to say, here's our drawing, here's our rod. Actually, I should make that part black. And now we can see at this end, the length is just L. And again, we're going to say this distance is R equal to X, and this thickness is dx, and lambda is equal to m over L, and dm is equal to lambda dx. So I is going to equal the integral from 0 to L of r squared dm, which equals the integral from 0 to L of x squared lambda dx. And that's going to give us lambda times the integral of x squared dx from 0 to L. And that's going to be m over L times 1/3 x cubed from 0 to L. And that gives us, of course, 1/3 m over L times L cubed. So I about the end is equal to 1/3 ml squared. And that's the formula we were looking for. And we got like 5 minutes left, so I want to tell you about the parallel axis theorem. The parallel axis theorem basically says the moment of inertia through a parallel axis is equal to the moment of inertia through the center of mass plus the mass times the distance the axis is away from the center of mass. So d is the distance away from the center of mass. So with that in mind, let's see if that's the case. I'm going to use this to verify the answer I just got. So I about the end is supposed to equal I about the center of mass, which I told you was the 1/12 ml squared. Now I'm going to take that and add to it the mass, which is big M, and then the distance from the center of mass axis to the axis that we are rotating about. That distance is L over 2. So I've got to square that. So I've got 1/12 ml squared plus 1/4 ml squared. 1/4 is the same thing as 3/12. So 1/12 plus 3/12 is 4/12 ml squared, and 4/12 is 1/3 ml squared, and that's I for the end. So you can see that now we verified that the parallel axis theorem is completely consistent with our derivation that we did. And that's it. Anybody have any questions on that? Okay, just remember, as I told you at the beginning of class, we do have a face-to-face test that's due this coming Sunday. I did mention to you that when you're doing the practice test, you might want to try using Microsoft Edge for your browser or Safari for your browser, because two students in my other class told me that when they switched to Microsoft Edge, they stopped getting the pictures not loading properly. And the other one said that when they used my Safari's browser, they didn't get the picture not showing up either. So that might help. It might not. That being said, I'm still replacing all those banks and erasing all the banks that I have in the course. And hopefully that doesn't cause a change to your practice tests. But if it does, then I want you to make sure you use the new practice test, and I'll send you an email about that to make sure, or email or announcement or something like that to make sure y'all know. You're free to go. I'm going to wait here till the last person leaves in case anybody has any questions. But thanks for coming, everybody. Thank you, Mahak. Sorry. You still have a question,
Um,
Sam? Yes.
yeah, I was probably just gonna do the same thing for the last test, just
Hmm.
uh because it works for me.
Which was the testing center or
Uh,
something?
yeah, the testing center. Last time for some reason Chesapeake didn't have any proctors, but that's okay. So I will send something out tomorrow if that's okay, and then I'll do the same thing. I'll forward it to you. So,
That's cool, no problem. Yeah, if the Chesapeake campus can't accommodate you, whichever campus is closer to you, that's fine. And I just send it out to either one. And once you make an appointment, they'll contact me and say, "Hey, we have a student coming such and such a day." So we just want it done. You could take it anytime, preferably Wednesday or later, but Wednesday, Thursday, Friday, Saturday, or Sunday would be allowed.
yeah, I don't think there's yeah, I'm thinking about doing Saturday. So,
Okay. That's cool. Make sure you
uh
can get an appointment with them, and like I said, I'll make sure I set up everything. Uh, Make sure you follow those instructions. I don't know how your test went last time, but remember, uh, as much as you give me on your work, that allows me to give you partial credit. So if you start off with an equation, go ahead and write the equation in its pure form, like it's seen on the equation sheet, and then show me it putting your numbers in, and then do the algebra or the calculus or whatever work you need to do to solve it. And that allows me, even if you use the wrong equations and stuff, it allows me to give you partial credit, that sort of thing. Make sure you show me very clearly your front and back of all your pages before the before the test starts, and then at the end, show me all your work and hold it still, and then slowly hold it still and try to show the whole screen. Ideally, I'd like to be able to just see the image on the actual Respondus video. So if you're showing me your work that way, that's best. But you still have to email it to me within 20 minutes after the test. Or they can send it to me since
um
you're doing a testing center. Sorry about that. I forgot. I went to put this up here, but yeah, that's all totally not related to you because you just finished telling me you're doing it at a testing center. So sorry about that, Sam.
no, it's fine.
I had a
Yeah, that was
rigmarole.
a
I had something I was going to tell everybody, and I just fit it in there, and it wasn't good fit. So I apologize.
no, I understand. Yeah, if not Chesapeake, I'll just do the Virginia Beach
Okay.
testing center.
I know we're having some short staff issues, so that might be the problem why they can't accommodate you at Chesapeake. But if they can't, hopefully they can. But if they can't, yeah, Virginia Beach will be fine or whatever. All right.
Y- Yep, yeah, they told me it's short staffing, so yeah, you're right.
Yeah.
All right, thank
Well,
you.
thanks, Sam. Have a good one. Good luck on your test, bud.
All right, thank you.
You're welcome. Bye bye.
Bye.
All right, and that's about it. So thanks for coming, everyone. Bye bye.